pick up a thick paperback novel right now. Like, literally try to open it flat on a table.
It won't let you.
No, it completely fights you. The pages bow up into this arch, and the second you let go, it just snaps shut like a mousetrap.
Right. And we just assume that's how books naturally behave.
Exactly. But it's actually this deliberate, aggressive act of industrial engineering. It's a specific compromise made decades ago just to save pennies on hot melt glue.
Yeah, it really is an invisible art form.
It is, because, you interact with printed materials every single day. You wake up, you stumble into a diner, you grab a menu, or you're flipping through a quarterly report at your desk.
Or curling up with a heavy hardcover at night.
Right. You consume the words in the images, but you're completely blind to the hidden physical architecture that actually holds all those pages together.
We just take it for granted that when we turn a page, it stays attached.
Today, we are decoding that invisible architecture.
These objects are vessels of information, and the raw mechanics of how they're constructed dictate so much of how you actually experience reading them.
Yeah, but the only time you ever notice the binding of a book or the fold of a brochure is when it fails.
Exactly. When a page falls out or a manual refuses to stay open while your hands are full, suddenly you're painfully aware of the engineering.
But when it works perfectly, it's entirely transparent. And to guide us through this invisible world, we are digging into Chapter 8 of an essential industry Bible. It's called Graphic Design Reference plus Specification.
Oh, this is the master playbook.
It really is. For designers, print shops, anyone who actually manufactures the physical media we consume, it strips away the romance of publishing and forces you to confront the math, the physics, and the material realities of paper and glue.
It's fantastic.
Now, before we get our hands dirty on the bindery floor, a quick reminder. If you're enjoying our deep dives, make sure to subscribe to the channel so you never miss an exploration like this.
Because honestly, after we get through today's session, you're going to want to feel these bindings and examine these folds for yourself.
Oh, absolutely. So if you want to get your hands on a physical copy of the book we're exploring today, you can either scan the QR code right there on your screen or just find the book link right below in the description. Okay, let's unpack this.
Let's do it.
Bindings and folds are not just practical necessities. They aren't some afterthought. Every time a designer decides to print something, they are entering into this brutal negotiation with physics, aesthetics, and economics.
And that negotiation is exactly what drives the entire printing industry. You have to ask yourself, do you want this object to last 100 years in a library?
Right.
Or do you need to produce 50,000 copies by next Tuesday for a supermarket checkout aisle?
Yeah, completely different goals.
Does it need to lay perfectly flat on a workbench so a mechanic can read it while holding a wrench? Every single one of those requirements pushes you toward an entirely different mechanical solution.
And every single solution requires a sacrifice. There is no magic binding that does everything perfectly.
No, it's a constant, high-stakes balancing act between form, function, and your budget.
So, let's start with the heavyweights of the bookshelf. The bindings that prioritize permanence and prestige above all else.
The luxury sedans.
Exactly. When you picture a beautiful heirloom hardcover book fighting for dominance on your living room shelf, you are picturing case binding.
Or, as the industry often calls it, Smythe Sewn.
Smythe Sewn.
Yeah, Smythe Sewn is the undisputed gold standard. It's the classic, time-honored method of building a proper book.
Okay, so how does it actually work?
Well, what's fascinating here is the sheer meticulousness of the architecture. You don't just take a giant stack of individual printer pages and glue them together.
Right, that would fall apart.
Exactly. You build the book out of modular units called signatures.
Okay, for anyone who hasn't spent time in a commercial print shop, think of a signature like a miniature booklet.
Yeah, that's a good way to picture it.
Imagine taking a massive single sheet of paper off a printing press. You fold it in half, then you fold it in half again, and maybe a third time. You end up with a small, neat package of nested pages.
Right. That single multiply folded sheet is one signature.
And a case-bound book is just dozens of these signatures lined up sequentially in a row.
Exactly. And the magic happens in how they're joined. You gather all those folded signatures side by side, and you physically sew them together.
Literally with needles and thread.
Literally. A specialized machine drives needles and heavy thread right through the folded spines of every single signature, linking them into one solid, interlocking unit.
Wow.
This creates what the industry calls a book block. But the sewing is only the foundation. Once you have this securely sewn block, you coat the entire spine in adhesive to lock those threads and paper folds permanently in place.
It's like weaving a tapestry. You have these interlocking threads building a highly unified, incredibly durable structure.
Yes.
But wait, at this point, all the pages are still folded shut at the edges, right? Like you can't actually open them to read.
Yeah, right. So the next step is entirely sculptural. The glued book block goes into a massive guillotine, and you trim the remaining 3 sides.
The top, bottom, and outer edge.
Exactly. You slice right through the outer folds, freeing the individual pages so you can actually turn them.
And this is where the case binding comes in, right?
Yeah.
Because the book block isn't glued directly to the outside cover.
No, the outer cover of the case is manufactured completely separately. It's heavy cardboard wrapped in cloth or leather or printed paper.
And the way they marry these 2 pieces together is brilliant.
It is.
They use end sheets. These are thick, specialized pieces of paper attached to the very first and very last signatures of your sewn book block.
Right.
They take those end sheets and glue them entirely across the inside of the hard outer cover. That thin layer of glue and end sheet paper is the only thing suspending that heavy book block inside the rigid case.
Yeah, it creates a beautiful hinge. And because the book is sewn in these nested independent sections, the spine is flexible.
So when you open it, the spine bows out.
Exactly. When you open a Smythe Sewn book, the spine acts like a series of individual hinges bowing outward. This gives case binding its most prized characteristic. It lays completely flat on a table.
That is the holy grail for a cookbook or a reference manual or an expensive art book. You don't have to hold it open with your elbow.
Right. Plus, the girth allowance is massive. You can build a hardcover up to 3 inches thick using this method.
3 inches, that's huge.
It is. It looks incredible, it has a printable spine, and it can easily survive for centuries.
But building a bespoke house like this comes with severe penalties.
Oh, absolutely.
It requires specialized machinery, it takes weeks of production time, and it is overwhelmingly the most expensive option on the market.
Yeah, you pay for that quality.
Furthermore, because you're relying on folded signatures,
Sure.
you are completely trapped by the math of the fold.
You absolutely are. You cannot just hand a printer a digital file with, say, 302 pages and ask for a case binding.
Why not?
Because if your signature is made up of a large sheet folded into 16 pages, your total page count must be perfectly divisible by 16.
I see.
So if your novel ends on page 302, you have 2 blank pages left over in that final 16-page signature.
And you can't just cut them out.
No, you cannot cut them out without destroying the integrity of the fold and the sewing.
Which is exactly why you open older hardcover novels and find 3 blank pages at the back that just say notes.
Exactly.
It isn't some artistic choice by the author. It's the inescapable math of the manufacturing process exposing itself to the reader.
Precisely. You either have to fill the paper with content or just leave it blank.
Okay, so case binding is beautiful, but it costs a fortune and takes forever.
Right.
If you're a publisher in the mid-20th century trying to get cheap paperback thrillers into every grocery store and airport in America, you can't wait for needles and thread.
No, you need a chemical revolution. You need brute force, speed, and massive cost reductions.
And that brings us to the prefabricated apartment block of the publishing world, perfect binding.
Perfect binding is an entirely different philosophy of construction. While case binding is like weaving a tapestry, perfect binding is like pouring asphalt over a dirt road.
Wow. Okay.
It is built purely for efficiency. Now, initially, the pages might still be printed and folded into signatures just to get them off the printing press quickly. But the very first thing the perfect binding machine does is aggressively destroy those folds.
It is shockingly violent. Like, I've seen videos of this. You take that entire stacked block of folded paper and you run the spine edge over a rotating roughing blade.
It literally grinds and mills away the folded edges, chopping the entire book down into a loose stack of single disconnected sheets.
It just chews up the paper.
Yeah, it chews it up to expose as many raw, microscopic wood fibers as possible.
And it has to be violent, right?
Yeah.
Because the success of the entire book relies on what happens in the next split second.
Exactly. Immediately after that spine is milled into a rough, fibrous texture, the machine rolls a thick, heavy layer of molten, hot-melt adhesive directly over the raw edge.
Oh, wow. So it's liquid plastic.
Yeah. Because the paper has been roughed up, that liquid plastic glue seeps deep into the cracks and anchors onto every single individual sheet of paper.
And then what?
While that glue is still scorching hot, the heavy paper cover is wrapped around the block, smashed firmly into the sticky spine, and the whole thing goes to a 3-knife trimmer to clean up the edges.
It's so fast.
Yeah.
And it can hold up to 2 3/8 inches of paper.
Right.
It's incredibly cheap. It is incredibly fast. And unlike case binding, because you're grinding off the spine anyway, you actually can bind loose single sheets together if you need to.
You can.
But let's be honest, the term perfect binding is a hilarious piece of 20th century marketing spin. There is absolutely nothing perfect about it for the reader.
No, it was perfect for the publisher's profit margins, certainly not for the user experience.
Right.
Because the fundamental reality of perfect binding is that you have taken hundreds of individual pages and encased their edges in a solid, rigid brick of dried plastic glue.
So it won't lay flat.
Therefore, a perfect bound book physically cannot lay flat.
This is exactly what we were talking about at the start of the deep dive, that mousetrap effect.
Yes.
To open a thick paperback, you are literally bending a plastic brick. You have to use both hands, squeezing with your thumbs, prying the pages apart, just to read the text near the center seam.
And that center seam is called the gutter. The tension of that glue block creates a critical design flaw known as gutter loss.
Gutter loss.
Yeah, because the pages are forced to bend sharply at the spine rather than hinging smoothly, a solid 1/4 inch or more of the page is swallowed by the dark crevice of the binding.
So if a designer isn't paying attention, and they print a gorgeous photograph spreading across 2 facing pages.
An entire vertical strip of that photo just disappears into the black hole of the spine.
You will never see it unless you physically snap the spine of the book in half.
Which breaks the glue block and causes the pages to start falling out like loose leaves.
So annoying, and this forces the designer to actively compensate, right?
Yes. They have to push all the text further out toward the outer edges of the page, creating unnaturally wide inner margins just to keep the words legible.
But the compromises don't stop at the margins. Perfect binding also dictates exactly what kind of paper you're allowed to use.
It does. It introduces a massive constraint regarding paper grain. The grain of the paper must run parallel to the binding edge.
Okay, let's explore this. I think most people assume paper is just a flat, featureless paste. But paper has a biology. It has a grain, just like a piece of wood.
It really does. If we connect this to the bigger picture of how paper is made, it makes perfect sense. Paper is manufactured from a wet pulp of millions of microscopic wood fibers floating in water.
Right.
As that watery pulp is pulled along a massive mesh belt in the paper mill, the water drains away, and all those tiny, needle-like cellulose fibers align themselves in the direction the belt is moving.
They line up.
They line up like logs floating down a river. That creates a distinct grain direction.
So if those microscopic logs are running up and down, parallel to the spine of your book, the pages will roll and bend relatively smoothly when you open it. You're bending with a grain.
Yes.
But if a print shop tries to save money by cutting the paper out of a parent sheet the wrong way, and those microscopic logs are running horizontally, perpendicular to the spine,
it is a disaster. You are effectively trying to bend millions of tiny wooden beams against their structural axis.
Wow.
The book will actively fight you. The pages will feel stiff, board-like, and resistant. The mousetrap effect we talked about will be magnified tenfold.
Okay, so to recap perfect binding, it forces you to use cheap adhesive, it eats your margins, it ruins crossover images, and it restricts your paper choices.
Yeah, it is the ultimate exercise in compromising user experience for the sake of mass production.
Okay, so if case and perfect bindings are the luxury sedans and the mass transit buses of the publishing world built for permanence, tick volumes, and bookshelves, what do you do when you just need to print a 16-page theater program?
Or a quarterly corporate newsletter.
Right. You don't fire up massive vats of molten glue or industrial sewing needles for 16 pages. You need the fast, utilitarian workhorses of the industry. You need wire stitching.
Or, as the rest of the world calls it, staples.
Staples.
Wire stitching is the unsung hero of the print world. It strips the entire concept of binding down to its absolute bare mechanical minimum.
It's incredibly reliable and ridiculously fast. And the undisputed king of this category is saddle stitch binding.
Yes.
Let's break down the mechanics of a saddle stitch, because while it looks simple, the geometry is actually fascinating.
It really is.
You don't collate pages into a flat stack. You go back to our old friend, the signature.
Yes. But instead of stacking folded signatures on top of one another, you open them up to their center spread and you nest them inside of each other.
Think of Russian nesting dolls. but made of folded paper.
Exactly. The innermost 4 pages are nested inside the next 4 pages, and so on, until the heavier cover sheet wraps around the entire V-shaped pile.
Then this entire nested structure is dropped like a tent over a metal rail, which the industry calls a saddle.
Hence the name.
Right. Mechanical head drops down, drives a piece of wire right through the center fold of all those nested pages simultaneously, bends the wire flat on the inside, and you're done.
The booklet is stapled right down the spine. You trim the 3 open edges flush, and it's ready to ship.
It's elegant in its simplicity, it lays remarkably flat, it's incredibly inexpensive, and it has a unique advantage, doesn't it? It easily accommodates loose inserts.
Oh, yeah. If a magazine wants to drop a loose perfume sample or a subscription card right into the center spread, they just let it fall onto the saddle before the staples fire.
That's so smart. But the physical limits of saddle stitching are absolute.
Yeah.
You cannot force it to do more than it was designed for.
No, you can't. The girth is severely restricted. You max out at about ½ an inch of thickness.
Because if you try to nest an inch of paper inside itself, the physics completely break down.
Yeah, the outer cover has to travel so far just to wrap around that massive chunk of inner paper that the spine will start to bulge outward like a balloon.
And the staples physically won't be long enough to reach through and crimp.
Right, and the tension will just tear the cover at the spine.
And beyond the thickness, there's a strict mathematical constraint that traps a lot of amateur designers. The page count absolutely must be in increments of 4.
I can't tell you how many times people try to design a 14-page or 15-page saddle-stitched zine.
It is literally impossible.
It is. Every single sheet of paper you fold in half automatically creates 4 distinct panels. A front, a back, an inside left, and an inside right.
There is no escaping it. Your page counts jump from 12 to 16 to 20 to 24.
But here's where saddle stitching introduces one of the most maddening physical hurdles in all of print design. It's a phenomenon called creep.
Creep? It sounds like a horror movie monster.
And honestly, to a designer who doesn't understand it, it is a nightmare.
So what exactly is creep?
Well, think about the geometry of nesting 20 sheets of folded paper inside each other. Paper is not infinitely thin. It has a distinct physical thickness.
Okay, sure.
The innermost folded sheet is sitting inside the next sheet, which is sitting inside the next. The combined thickness of all those outer sheets physically pushes the inner sheets outward.
So if you were to look at the open edge of the booklet before it goes to the trimmer, it's not flat.
No, not at all.
The inner pages are physically sticking out further on the right side than the outer cover. They form this sharp, protruding arrowhead shape.
And that outward geometric displacement is creep.
Right. Now, to make the booklet look professional and neat, the printer puts it under a masked guillotine blade and slices off that entire protruding arrowhead so the edge is perfectly flush.
Which sounds completely reasonable.
Until you realize what that blade just did to the artwork.
Exactly.
If the inner pages were pushed out a full 1/4 inch past the cover and you chop them all flush, you just sliced a 1/4 inch off the outer margin of your center pages.
Yeah, if you had a page number sitting near the edge or text running close to the margin, the trimmer just chopped it in half.
The reader opens to the center spread, and the words are literally missing.
It's catastrophic for the layout.
So how do you fix it?
To solve this, the designer has to mathematically calculate the exact creep based on the microscopic caliper thickness of the specific paper stock they're using.
Wow, really?
Yes. Then they have to incrementally shift the artwork of the inner pages inward, closer and closer to the spine, to compensate for the push.
That sounds incredibly tedious.
It is. But so when the blade finally comes down, the remaining margins all look perfectly identical to the naked eye. It's an incredible amount of hidden spatial math.
I love that. You think you're just putting a staple in some paper, but you're actually calculating geometric displacement across 3-dimensional space.
Exactly.
Okay, so saddle stitching is the elegant nested option, but there's another wire stitching method that throws elegance out the window entirely. Side stitch binding.
Oh, side stitching is the pure brute force approach.
Yeah, you completely abandon the nesting dolls concept.
Right. Instead, you collate the loose pages into a single, flat, squared-off stack, exactly like you would for perfect binding. But instead of gluing the edge, you take a heavy-duty wire staple and drive it straight down through the face of the entire stack, maybe a 1/4 inch in from the bound edge.
It's essentially an industrial nail gun for paper.
Pretty much.
It can blast through up to a full inch of solid paper stock, which is double the capacity of saddle stitch.
Yeah.
It is ridiculously fast, incredibly cheap, and you can use heavy wire gauges.
But
But Looking at these specs, I have to ask, why on earth would anyone subject a reader to this? It explicitly states that the pages will never lie flat. You are literally bolting the pages together from the top down.
Yeah, it's brutal.
Furthermore, you have to leave a massive 1-inch blank margin on the inside of every page just so the text isn't swallowed by the staple hinge.
It sounds incredibly user-hostile.
It is entirely user-hostile. It is ugly, it is stiff, and it is awkward to read.
So why use it? Well, you have to remember that matrix of trade-offs we talked about. You are knowingly sacrificing every ounce of usability and aesthetic beauty for two things: blinding speed and absolute indestructible durability.
Okay.
A side-stitched document is a tank. The metal wire loops through the entire solid block of paper. Those pages will never, ever fall out.
So where do we actually see this in the wild?
You see it where survival matters more than looks. Industrial manufacturing logs, massive, hundreds of pages long legal briefs, auto repair manuals.
Documents that are going to get beaten up.
Exactly. Documents that are going to be thrown into a greasy toolbox, shoved into a filing cabinet, dropped on a concrete floor, or handled by 100 different people on a factory line.
They do not care if it lays perfectly flat.
No, they care that page 42 doesn't go missing when they need to rebuild an engine. Because it avoids the complex folding of saddle stitching and the messy drying time of perfect binding, a print shop can churn out side-stitched industrial documents at an astonishing rate.
Okay, that makes perfect sense. It's the indestructible tank. But what happens when we need a document to be alive?
What do you mean by alive?
Like, what if the document has to evolve over time? Or what if a designer wants to combine completely incompatible materials?
Ah, right.
Say you want a heavy sheet of brushed aluminum for a cover, followed by a sheet of delicate translucent vellum, followed by standard thick cardstock.
Right, hot melt glue won't anchor to aluminum uniformly, and side stitching might crack the vellum?
Exactly. When we need that level of control, we have to move away from fusing the paper and move into mechanical modularity. We are entering the realm of mechanical and tape bindings.
This represents a massive philosophical shift in how we treat the materials. We are no longer trying to turn paper into a single, seamless block.
We're treating the pages like individual building materials that need to be bolted or looped together.
Exactly. Let's start with the one hybrid in this category, which bridges the gap between glue and mechanical hold: tape binding.
Right. Tape binding feels very academic. You see it on university dissertations or in-house corporate reports.
Yeah, you assemble your signatures and covers, trim them flush, and then you take a strip of heavy, flexible cloth tape that has a heat-activated adhesive embedded in it.
You wrap that tape over the spine, apply heat, and the melting glue binds the covers and the paper together.
It's a fascinating middle ground. Like perfect binding, it uses a block format and heat-activated glue. But instead of wrapping a full printed paper cover around the entire book, the spine is just this functional strip of colored cloth tape.
It can handle up to 1 3/4 inches of girth. It lays reasonably flat, and the cloth spine makes it highly durable for a moderate cost.
It has a very specific utilitarian aesthetic.
It does, but it still relies on glue. If we want true, absolute mechanical fastening where we can tear the book apart and rebuild it, we have to look at screw and post binding.
Now we are literally bolting the book together with hardware. In screw and post binding, you take your stack of loose pages and covers, trim them perfectly flush, and you use a specialized paper drill bit to bore holes straight through the entire stack, right along the binding edge.
Then you insert metal or plastic posts through those holes and screw a cap onto the other side to clamp it all together.
It holds up to 1 inch of material. It is incredibly durable, but it comes with a high cost.
And, very much like the side stitch, it absolutely does not lay flat because you physically clamped the inner margin together with bolts.
But the superpower of screw and post is completely unmatched.
Unmatched updatability.
Yes, if a high-end restaurant has a heavy embossed leather menu bound with brass screw posts, and they need to update the wine list,
They don't throw the menu away and print a new one.
they simply unscrew the binding, pull out the outdated page, drop in the newly printed wine list, and screw it back together. It's infinitely modular.
And it completely solves the mixed materials problem. Because the posts are just threading through a drilled hole, the binding mechanism does not care what the material is.
Not at all.
It will clamp a sheet of wood to a sheet of plastic just as easily as it clamps 2 pieces of paper.
Exactly. But you have to pay for that luxury and labor. You cannot automate the process of a machine threading tiny, delicate screws into metal posts across a print run of 5,000 books.
It's an intensely manual, hand-assembled process.
Yeah, that makes it completely inappropriate and cost-prohibitive for large commercial print runs. It is strictly an artisanal, premium short-run solution.
So if screw and post is too labor-intensive for a run of, say, 500 corporate training manuals, but we still need the pages to be individual and somewhat modular, we inevitably turn to the punch and bind methods.
The office classic.
Exactly. These are the mechanical bindings everyone has seen in an office supply closet or a school presentation. The plastic comb, the spiral wire, and the ring binder.
Let's start with the ubiquitous plastic comb.
The plastic comb is the ultimate hallmark of the short-run corporate document.
It really is. A machine punches a row of rectangular holes along the edge of the paper stack. Then, a mechanism spreads open a cylindrical plastic comb, inserts the plastic teeth into the holes, and releases it so the plastic curls back onto itself, trapping the pages inside the cylinder.
It can handle a solid 1 3/4 inches of paper. It's very cheap for small runs, and crucially, it lays completely flat on a desk.
Right.
And unlike perfect binding, if you open to a center spread, the left and right facing pages align perfectly with each other.
Technically, you can pry the comb back open to add or remove a page, though it's always a bit of a wrestling match.
It is. Functionally, it does exactly what it needs to do. Aesthetically, however, it is universally considered very low end.
Yeah, it's not winning any design awards.
And while the plastic combs themselves are cheap, the hand assembly required to line up the punched holes and operate the comb spreading machine makes it surprisingly slow and costly if you try to scale it up to thousands of copies.
Which brings us to the massive step up in quality: spiral and double loop wire binding.
The concept is similar. Punch holes and thread a binder through, but instead of a cheap plastic comb, you're threading a continuous spiral of plastic or metal wire.
Or a C-shaped double wire loop that is mechanically crimped shut.
Wire binding is incredibly durable and professional. It handles up to 2 inches of paper, and it has one distinct advantage over almost every other binding.
It doesn't just lay flat, it can fold completely back on itself 360 degrees.
Right. If you're printing a workbook, a journal, or a manual where the user only has room to look at one page at a time, wire binding is unparalleled. Here's where it gets really interesting. I was looking at the limitations column for spiral binding in the text, and it highlights a physical quirk that I had never considered, but it must be absolutely maddening for a designer.
Oh, the jog.
Yes, because a spiral is, by definition, a continuous coil winding its way upward along the spine. The holes on the left page don't line up horizontally with the holes on the right page.
No, the wire's traveling at an angle. So when you open the book, the pages jog.
Jogging is a brilliant mechanical detail to highlight. As the wire angles upward from the left page into the right page, it physically pushes the right-hand page slightly higher than the left-hand page. They shift vertically.
So what does this all mean for the layout?
It means that if a designer creates a beautiful continuous photograph or a bold headline that crosses over the spine from the left page to the right page, the layout will break.
Yep. The right half of the image will sit a fraction of an inch higher than the left half.
A face will be severed and misaligned.
A designer sitting at a computer looking at a perfectly flat, mathematically flawless digital spread has to mentally project the physical angle of a metal coil in the real world to know if their artwork will survive the binding process.
They must actively avoid crossover designs or design them to tolerate that vertical shift.
It is the perfect example of invisible architecture dictating creative choices.
I love that. Finally, rounding out the mechanical category, we have the ultimate modular system, the ring binder.
The standard 3-ring binder. It's the workhorse of the classroom and the filing cabinet.
It holds massive girth, easily up to 3 inches of paper. It is low cost, lays flat, and offers total effortless modularity. You just snap the metal rings open and snap them closed.
But as with the screw posts, hand assembly makes it a nightmare for large commercial runs.
Right. It's designed for in-house assembly or for situations where you mail the end user a stack of pre-punched updates and expect them to put the pages into the binder themselves.
Precisely. You don't buy a fantasy novel in a 3-ring binder. It entirely lacks the permanence, the cohesion, and the object quality of a true-bound volume. It's merely a container for loose pages.
Okay, we have explored how to sew, glue, staple, bolt, and coil pages together. But to execute almost any of these methods, especially case binding, perfect binding, and saddle stitching, we need signatures.
And to create a signature, you have to fold paper.
You can't bind a signature if you don't know how to fold it. But as we discussed earlier with paper grain, a sheet of paper isn't just a blank, featureless void.
It is a physical object with anatomical properties. It has a biology.
Let's move into the physics of the fold.
This is where the engineering gets microscopic. When most people think of folding paper, they just think of creasing a line. But the text begins by breaking down the fundamental binary of folding.
Every complex origami structure, every intricate brochure is made up of just two basic actions: valley folds and mountain folds.
It sounds like map making, topography.
It is exactly like topography. A valley fold creates a trough. The crease dips down away from you. A mountain fold creates a peak. The crease pushes up toward you.
Right. By sequencing mountains and valleys, you create structure. But as you said, paper has a biology, and the absolute nemesis of a clean structural fold is paper grain.
We touched on this when we talked about the mousetrap effect in perfect binding.
Okay.
But the text goes into incredible detail here regarding folds.
It does.
It explicitly states that heavy text and cover-weight paper absolutely must be scored before folding. And crucially, it must be folded in the direction of the grain.
If we connect this to the bigger picture, think about what's physically happening when you fold a thick, glossy piece of cardstock.
You're putting it under a lot of stress.
You're subjecting that paper to extreme stress. You are violently crushing the cellulose fibers on the inside of the fold, and you are stretching the fibers and the clay coating on the outside of the fold.
And if the paper is thick, that stretching exceeds the material's tensile limit.
The coating and the fibers simply tear apart, leaving an ugly, jagged, white cracked line right down the middle of your dark, beautifully printed design.
Okay, the text says we had to score the paper first to prevent this. I always thought scoring just meant pressing down really hard with a bone folder while you folded it.
No, not at all.
Looking at the mechanical specs here, scoring is an entirely separate step before the fold even happens, right? You are pre-crushing the paper.
That's exactly right. Scoring uses a blunt metal wheel or a steel rule to press a deep, uniform groove into the paper exactly where the fold will eventually go.
It safely pre-crushes the fibers, creating a weakened hinge point.
That way, when the paper is finally folded, it bends cleanly along that hinge rather than breaking haphazardly across the surface.
But even with a heavy score, the text warns that folding against the grain is asking for trouble.
Because if those microscopic wood logs we talked about are running horizontally across the page and you try to fold the page vertically, you're literally trying to snap millions of tiny wooden beams in half simultaneously.
Ouch.
The paper will fight you. The fold will be bulky, uneven, and prone to cracking, even with a score.
But if you fold with the grain, you're just gently parting the logs, allowing the paper to bend cleanly along its natural axis.
Exactly.
The source actually provides a brilliant practical DIY test for this. I want you to try this right now if you have a piece of standard printer paper nearby.
Oh, this is a great test.
Take the sheet and fold it in half vertically, creating a tall, skinny shape. Give it a good, sharp crease with your thumbnail. Now open it back up and fold it in half horizontally, creating a short, wide shape. Crease that one too.
Okay.
If you close your eyes and gently run your fingertips along those two intersecting folds, you will feel a distinct physical difference.
One fold line will feel incredibly even, smooth, and compliant.
And the other will feel slightly bulkier, rougher, or less crisp.
That smooth, compliant fold is the one running parallel with the paper grain. You can literally feel the microscopic alignment of the wood fibers translating into physical resistance.
It is a phenomenal little experiment. It proves that paper is an active participant in the design process. It has a will of its own, and if a designer or a printer doesn't respect the grain, the final product will feel fundamentally amateurish.
It really will.
So, armed with the knowledge of grain, valleys, and mountains, how do we actually manipulate the paper? The source outlines a very specific geography of folds.
It dictates standard industry terminology that you absolutely must use.
You can't just call up a print shop and say, hey, fold this like an accordion fan thing.
No, you need the exact terminology, or you will get a palette of ruined brochures.
Let's map out this geography, moving from the simple to the complex, starting with the 4-page folds.
This is the simplest manipulation of a sheet of paper possible. A simple fold is one single fold made along either the short or the long dimension of the paper, splitting it in half and resulting in 4 distinct panels or pages.
But then there's the 4-page short fold. This is a brilliant variation because it introduces intentional asymmetry.
It's a single fold, but it is made entirely off-center, leaving 2 panels noticeably wider than the other 2.
Why would a designer choose to do that?
It's a classic, highly effective trick for pacing and reveals. Imagine a corporate brochure where the front cover panel is half an inch narrower than the inside back panel it rests against.
Okay.
That exposed vertical strip of the back page creates a visual teaser. Maybe it's a bright flood of color or a provocative question that peeks out from behind the cover.
It breaks the expected symmetry of a booklet and practically demands that the reader open it to see the rest. Okay, moving up in complexity. We hit the 6-page folds. This requires 2 parallel folds to create 6 distinct panels. And there are 2 main ways to execute this, representing 2 fundamentally different user experiences.
The first is the accordion, or Z-fold.
The accordion fold is exactly what it sounds like. It uses 2 simple folds, but they bend in opposite directions. A mountain fold, followed by a valley fold.
It creates a zigzag shape, like the letter Z. The great thing about accordion folds is that they are infinitely scalable. You can keep adding alternating folds to create a long, continuous strip of 8, 10, or 12 panels.
The user experience of a Z-fold is very energetic. Because the folds alternate, the brochure naturally acts like a spring. It wants to pop open.
You can pull it completely open into one massive continuous timeline, or you can read it page by page.
But the alternative 6-page fold is the barrel, or roll fold. And this is a completely different psychological mechanism.
Instead of alternating mountain and valley, the barrel fold uses 2 valley folds.
Okay, so they fold in on each other.
Right. The outer edges of the paper both fold inward toward each other, rolling up into a tight, flattened cylinder. The right panel folds inward to cover the center panel, and then the left panel folds inward to cover the right panel.
It creates a sense of depth, a sense of discovery. You have to actively unroll it, peeling back layer by layer to get to the core message buried inside.
And the text notes that if you keep rolling it up with more than 6 panels, it becomes a rolling fold.
Yes. But as we're going to explore in a moment, the barrel fold introduces a terrifying mathematical trap that the springy Z fold completely avoids.
But before we get to the math of the fold, let's finish the geography with the 8-page folds and beyond.
8 pages require 3 folds. The first one is the parallel fold. The source describes this as a hybrid, a combination of a barrel fold and an accordion fold.
Think about folding a sheet of paper in half and then simply folding it in half again in the exact same direction.
It creates a bulky, very compact shape. You often see this used for incredibly dense informational inserts, like the massive, tiny text instruction manual crammed into a tiny pharmaceutical pill box.
Then we have the 8-page gatefold. This is pure drama.
Oh, I love a gatefold. It's essentially a barrel fold, but with one additional fold right down the dead center.
Visually, it is the most theatrical fold you can use. You look at the front cover, and it's physically split right down the middle, like a set of grand double doors, a gate.
You grab both edges, and they swing outward in opposite directions to reveal a massive, expansive, uninterrupted spread inside.
It's used for high-impact centerfolds in magazines or luxury real estate brochures where you want a wow moment.
And finally, the text brings us full circle back to the very beginning of our deep dives, the 8-page French fold, which scales up to become the 16-page signature.
This is crucial.
I want to describe this visually for you, the listener, because it ties everything together. Imagine taking a large, flat sheet of paper. You fold it in half vertically. Now, instead of folding it in that same direction again, you rotate the paper 90 degrees and you fold it entirely perpendicular to the first fold. You fold the fold.
Exactly. You are crossing the axis of the folds.
This specific configuration of crossed perpendicular folds is the exact mechanical method used to create the 16-page signatures needed for the case binding and perfect binding we discussed in Section 1.
This is how the bespoke house is built. It starts right here, with perpendicular folds creating those nested pages.
It's the foundational building block of the entire publishing industry.
But, and this is where the text gets incredibly granular, folding sounds simple and neat until you run headfirst into the physical reality of paper thickness.
Right.
You can sit at a computer and draw a perfect gatefold or a perfect barrel fold in your design software, dividing your digital canvas into perfectly equal thirds or quarters.
But if you actually try to fold real physical paper into perfectly equal thirds and attempt to nest one panel inside the other,
it catastrophically fails.
Which brings us to the hidden math, the final microscopic layer of our invisible architecture. The tolerances for overlapping folds. You literally cannot fold paper perfectly into thirds if the panels have to tuck inside one another.
No, you cannot. Think about the actual physical thickness of a sheet of 80-pound cover stock. It is a three-dimensional object with volume.
Okay, let's visualize this.
Let's say you have three panels, A, B, and C, and you design them to be exactly 3 inches wide. If you try to fold panel C inward so it lays flat against panel B, that works fine.
Sure.
But then you try to fold panel A over the top of panel C to close the brochure. Panel A has to travel across its own 3-inch width, PLES, and it has to climb over the physical wall created by the folded edge of panel C.
It will physically run out of paper before it reaches the other side.
The outer edge of panel A will crash violently right into the inside fold of panel C. The whole piece of paper will buckle, warp, and violently refuse to close flat.
It will look like a bloated, springy mess. That tiny fraction of a millimeter of paper thickness becomes an impassable wall.
The source text provides the exact mathematical tolerances required to prevent this disaster, specifically calculated for standard text weight paper.
Let's look at the gatefold tolerances first.
To stop those grand double doors from crashing into each other when they close, the text specifies that gatefolds require a subtraction of exactly 1/8 of an inch, or 3.175 millimeters, on the outer panels in the fold sequence.
So the two panels that actually form the doors of the gate have to be physically narrower than the massive back panel they're covering.
Exactly. The central panels must be wider. If the inner panels are 3 and 18 inches wide, the outer gate panels must be shrunk down to exactly 3 inches wide.
By shaving off that 1/8 of an inch, you give the outer doors the necessary spatial clearance to fold inward and lay perfectly flat without their edges colliding in the dead center.
But the roll or barrel fold tolerances are even more complex. It's not just a single adjustment for 2 doors, it is a cascading sequence of shrinking dimensions.
The source dictates that each panel in the sequence must be exactly 1/8 inch, or 3.175 millimeters, smaller than the panel that wraps around it.
Let's visualize this without getting bogged down in raw numbers. The absolute numbers don't matter as much as the fundamental rule. Every single time a panel tucks inside another panel, you must shave 3 millimeters off its width.
Imagine a 4-panel barrel fold. You are rolling the paper up.
The very innermost panel, the one buried at the core of the roll, must be the smallest. The panel that wraps over it must be larger to accommodate climbing over that paper wall.
The panel wrapping over that must be larger still.
To the naked eye, the finished folded brochure looks perfectly symmetrical and mathematically balanced. But if you took a ruler and unfolded it, you would find a hidden, descending staircase of shrinking measurements.
So what does this all mean? It means that graphic design is not just about choosing cool fonts and putting pretty pictures on a flat screen.
The digital screen lies to you.
It does. The screen shows you flat, weightless, mathematically perfect geometry. But reality is a physical three-dimensional space governed by friction, tension, and volume.
Designing a simple folding brochure is actually an exercise in precise spatial mathematics and physics.
If a designer doesn't know about that cascading 1/8 of an inch, if they just divide their canvas equally by 4 and email it to the printer will try to fold it, the inner panels will crash into the folds, the paper will buckle, and an entire print run of 10,000 brochures is instantly, irrevocably ruined.
And it will be completely unusable. And the printer won't take the blame, nor should they, because they printed exactly the flawed geometry they were given.
The responsibility of understanding this invisible architecture falls squarely on the creator.
That is why texts like this reference guide are so utterly vital to the industry. They anchor the weightless digital dream to the harsh physical reality of the bindery floor.
It is incredible. We have covered so much ground today. We started with the sheer permanence and bespoke weaving of Smythe Sewn case binding, building massive books meant to last lifetimes.
We explored the violent efficiency of perfect binding and its hot melt glue.
We moved to the utilitarian, lightning-fast, nail-gun speed of side stitching, built purely for survival in a mechanic shop over aesthetic beauty.
We explored the mechanical oddities of screw posts and spiral wires, where the physical angle of a coil causes pages to jog and shift, actively demanding the designer's awareness and altering their layout choices.
And finally, we zoomed all the way down to the microscopic level. We looked at the natural alignment of wood logs in the paper grain and the absolute spatial necessity of shaving an 1/8 of an inch off a panel just so a barrel-fold brochure can exist in three-dimensional space without destroying itself.
It is a profound level of detail that hides in plain sight every single time you pick up a menu, a magazine, or a novel. But connecting all of this to the bigger picture raises an important question, something I think we should all ponder as we interact with information moving forward.
What's that?
We have spent this entire deep dive discussing the physical constraints of paper, folds, and bindings. We've talked about the friction of the grain, the dark gutters of perfect binding, the page count limitations of saddle stitching, the weight of the paper, but we live in an increasingly digital age.
Right.
Today, a page is often just an infinite, frictionless scrolling screen on a phone or a tablet, completely devoid of physical limitations. When we lose that architecture, do we lose something fundamental to the reading experience?
Wow.
Historically, the pacing of a narrative, the drama of physically turning a page, the enforced pause of opening a gatefold were all dictated by these exact binding constraints. When those physical constraints disappear completely into the ether of a glass screen, does the way we consume, process, and retain knowledge fundamentally change?
Wow. That is the perfect thought to chew on. When you remove the architecture, the walls, and the foundation, does the house still feel like a home? I absolutely love that. And I want to thank you, the listener, for joining us on this incredibly detailed, tactile journey today.
It's been a blast.
I hope the next time you pick up a thick paperback and have to pry open that stiff gutter just to read the text, you don't just get annoyed. I hope you smile and think about hot melt glue, milled spines, and the industrial compromises made to get that story into your hands.
Just remember the perfect binding machine.
Yes. If you enjoy decoding this invisible architecture with us, please make sure to subscribe to the channel for more explorations into the hidden mechanics of the designed world.
And remember one last time, if you want your own physical, expertly bound copy of Graphic Design Reference plus Specification to study all these tolerances, folds, and diagrams for yourself,
just scan the QR code on your screen right now or click the link right below in the description. Keep looking closer at the physical things you hold in your hands. We will catch you on the next deep dive.